Hello everybody and welcome to our new C3D Development Conference 2022. Hope you enjoyed the short video which played before. By the way, you can leave some comments about it in our chat. You can find it right in the broadcast window. And before we start, I think we should introduce ourselves. My name is Artyom.
Hello everybody, my name is Ekaterina. Well, today we are going to show you what is new in our C3D Toolkit. Our developers will be pleased to tell you in detail what changes we brought to our components, how many new tools we developed just in last year, and much more. We also invited special guests who are our customers. They will share their experience on how they use toolkit models with their products.
At the end of the conference, we are going to demonstrate you how to use our components in real time. 2 our colleagues and 2 workshops with examples and code fragments. It especially fits those who just begin to use our components and want to know more.
Also, I think we and our team are interested to know from which places are you looking at us now, so please write names of your cities in the chat. And so our event will take about 3 hours. You can write down your questions during the conference and our team will get back to you.
So I think we can move to the main part of this conference, and I'm glad to invite our first speaker. Please meet Oleg Zykov, CEO at C3D Labs. He will tell you about our company's update.
Hello friends, thank you so much for joining our conference today. Before passing the microphone to our developers, I will show you a short company's update. Let's start from our history, if you don't know about us. We started the development of a C3D kernel in 1995 in our parent company Ascon. In 2000, the first product based on our kernel, Compass 3D V59, was released to the market. After that, for a long time, we was a mathematician team in a Compass development team. But 10 years ago, Ascon made a decision to establish a spin-off, a separate company, C3D Labs, to make our kernel available for all other developers in the world. So this year we celebrate 10 years anniversary. 10 years ago, we was a company with just 10 employees. We had 3 modules, Modeler, Solver and Converter, and we had only 1 customer, Compass 3D. After 10 years, we have more than 40 employees on board, including 9 PhD, and we are working from 3 different locations. And the main thing that we have 55 customers from 14 countries who use C3D Toolkit to develop their own engineering software. And our main goal is to make all these customers happy. Each year we solved more than 1,000 customer requests. These are not only bug fixing, we develop new features based on customer requests, we upgrade current functionality and do a lot of work with our customers. But we not only improve current solution, we release new modules in our toolkit. For example, last year we released a C3D Fair Curve Modeler, the innovative solution for developers of engineering software. It helps you to modeling curves that we call functional curves, because they are much better than A-class curves that you know from other vendors, and they help you to improve functionality of your products. On a screen you can see on the right side the curvature graph of a F-curve in a C3D, and it looks amazing. And on the left side the curvature graph from another software, and it's not so good, but it's A-class curves. Another solution from our company that we released last year is a C3D Web Vision. We already have a desktop solution for visualization of huge CAD models, and now we bring this functionality to the web. and it helps you to develop your own web application that can work with the huge 3D models in a manufacturing field or in building information modeling. Thanks to our developers and to our products, and of course to all our customers. And last year was the most successful year in our history. We doubled our revenue on the C3D Toolkit sales. And this year we continue our growth. Thanks for everyone who believe in us and use our software. Now I want to tell you about several new customers who decide to use our kernel during last year. Not everyone gave us a right to do that, but several companies did this. First is Adam. This is a well-known company, developer of computer-aided design and computer-aided manufacturing software. They decided to switch from one kernel, from ACES to C3D. This is a very challenging thing. We know about that because several years ago another customer, Nanosoft, did the same. And we try to help our colleagues to go through this process. Next customer is Numerical Calculations Russia, developer of a turbo research and design software. This is a very special software to design and analyze turbo machine blades. You know that the blade is one of the most difficult parts in the manufacturing industry. Let's go to the building information modeling. You know that our components can use in any industry because geometry is a very universal thing. This company, Project Point, is a developer of an environment for engineering, design and construction management. They use C3D Web Vision for visualization in their web application. Our customers who use kernel for many years continue to release new versions of their product and continue to improve their functionality based on our kernel. One of examples is Logos Prepost, computer-aided engineering software from Rosatom. In a new release, they add a lot of new functionality from C3D kernel. One of them is a 3D model simplification that based on our direct modeling, and another one is a medial shell functionality that we develop by their requests. It's a new function that we did special for them, and now this function available for all our customers. And of course, Ascon. I started my presentation from Compass 3D, our first customer, the main product of our parent company. This year they released a Compass 3D V21, new release of this software. And in this release you can find also a lot of functionality based on the kernel functions, like complex surface modeling or complex sheet metal modeling. The strategy of Ascon is to bring this product to a high level from a mid-range software, and a lot of things we did in our kernel to achieve this goal. So this is a part of our strategy. Also, of course, we listen to all our customers and put their requests to our roadmaps. Also, we look at industry trends and do some new things, new features in our software. For example, today you will hear about improvement in polygonal modeling in our BREP kernel. This is one of the things that we do. And also we based on our own expertise like C3D fair curve modeling, that is completely our own know-how. That's what we do, and that's what we will do in the future. Thank you so much and have a good conference.
Thank you, Oleg, for the great start. It's always good to know how the business works. And our next speaker was recently promoted to head of C3D Labs development. Congratulations, Yuri Kazulin. and he will tell you about novelties of C3D Toolkit. Please start.
Good afternoon, colleagues. My name is Yuri Kazulin, and today I would like to tell you something in a new role for me. There have been a number of changes in our development team. I'm now the head of the kernel development as a whole, and Andrei Tumanin, instead me, is the team lead of the geometric modeling team. Our team continues to grow, filling the kernel with the new functionality and performing improvements to existing ones. This year, to improve and accelerate your technical support, a separate technical support and documentation team was recently created. As part of technical support, you will now interact more often with not developers, but with support service employee Maxim Kulagin. But direct communication with developers is still possible. Now, a little bit about the kernel for the year for each of development areas. What's about Modeler? So what's new in the geometric modeler team? The main direction of development are as follows: surface modeling, direct modeling, and polygonal modeling. In the future, with a possible transition to hybrid modeling. In surface modeling, new types of surfaces and diagnostics of the smoothness of joining surfaces have appeared. The functionality of the patch operation was additionally improved. And there are new possibilities for curves and surfaces prolongation. Solid modeling can be mentioned in the context of new fillet and Boolean operation abilities. In direct modeling, the improving of functionality was continued, and works are planned with processing of significant changes in topology. Polygonal modeling is developing in the areas of the Boolean operation, diagnostics, and projection of polygonal shells. Andrei Tumanin will tell you more about this in details. Next, let's move on to the converter team. The main changes here are converter meshes from STL to JT representation, preliminary downloading of the attributes lists, version management of conversion plugins for different datasets and their representation. And of course, the team is continuing working on import and export processing quality. Alexander Spivakov, converter team lead, will tell you more about it. So then let's move on to the Solver team news. I will brief here. Improved redundancy diagnostics, increment dimension, and collision detection, they are the main direction of the development in the Solver model. Also, the team is working on performance of big mating dataset. I guess Sergey Belov, Solver developer, will introduce you to new Solver products and improvements. And finally, let's focus on vision and viewer team achievements. Novelties and improvements to the vision model are the next. The orientation maker scene orientation control tool has been improved. Update of the object selection to mouse picking were performed. The new explosion tool intended to simply examining the composition of the model is in its final stage. As for web vision implementation, geometry search and PMI comments and linear dimension were added. Also, dynamic cutting of the model has been added, and performance of instances geometry processing was improved. Basic changes to the viewer application are the next. Linux operation system support for the viewer application has been added. Changes in the graphic user interface to optimize the representation of the interface were performed, and the functionality of the professional version in terms of the ActiveX plugin has been extended. Section planes functionality was also improved. Ability to quickly find components based off model graphs was added. The developer of Vision team will touch you to novelties and improvements in their Web Vision module. And that's all I would like to tell you. Thanks you for attention.
Well, thank you, Yuri. It was good to hear about overall changes in C3D Toolkit. And now I'd like to introduce the next speaker, Andrei Tumanin. He will show us new and improved tools in C3D Modeler and present brand new polygonal modeling for our kernel. Andrei, please join us here.
Feature update for C3D Modeler 2022. As an introduction, I want to say a few words about what a C3D Modeler component is. Next, I'll talk about the new features in C3D Geometry Kernel and present some plans. Finally, I will introduce the new kernel features for polygonal modeling. So, C3D Modeler overview. C3D Modeler is a high-performance geometric kernel designed for 2D and 3D modeling. To build a geometric model, C3D Modeler uses curve modeling, surface modeling, solid modeling, direct modeling, unique sheet metal modeling component, and at the moment we are actively expanding our polygonal modeling capabilities. C3D Geometry Kernel provides the user with an impressive set of various methods for constructing and modifying geometric objects. There are, for example, Boolean operation, fillets, sweeping, rotation, and so on. Also, C3D Kernel allows to perform calculations on building triangulation for model visualization, obtaining flat projection of a geometric model, calculating mass inertial characteristics, and detecting collisions. Next, I begin a review of changes in C3D kernel for the year. Let's start with curve modeling. Curve modeling activities performed by our team include functionality for unwrapping surface curves onto a plane, new operation for chamfering at the joints of three-dimensional contour, new curve extension functionality with given parameters, NURBS curve fitting by points with smoothing. The module for constructing fire curves was also actively developed. Also, the possibility of custom reparameterization of curves was implemented. Some improvements were made in the projection curve in terms of calculating higher order derivatives. And finally, the optimization of construction of contours enveloping the points was carried out, as a result of which the acceleration of this operation was obtained up to 1 order. I will highlight some position in more detail. On the left is the result of unwrapping surface curves from a cylindrical surface to a plane. On the right, the result of chamfering at the junctions of a three-dimensional contour. By the way, this improvement was made at the request of one of our customers at the last C3D DevCon. A new curve extension operation is currently under development. Elongation occurs beyond any of the end of an open curve by given length value in following ways. First, with a tangent extension. In general, the result is a line segment that forms a contour along with original curve. Second, with an extension by circle arc. The expanded section of the curve is an arc of circle, which also forms a contour together with the original curve. Finally, the third way, elongation is carried out according to the parametric law of the curve. For curves that do not have an analytical extension, the extension is performed with a smooth change in curvature and torsion. When extending with an option along the surface, the resulting curve remains lying on the surface. A new approach has been implemented for approximating the NURBS curve of an ordered set of points with given parameters of accuracy and smoothness. Our plans for the development of curve modeling in the near future include wrapping a flat curve onto a surface. This is the inverse problem to the unwrapping of the curve that I already mentioned. We also plan to improve the curve extension functionality. The Fire Curves module will be further developed. The problem of rotating a part of the curve relative to the fixed point will be investigated. Next, consider in the surface modeling component. The main activities in this area are ruled surface new construction methods, improvements of swept surface with conic section. Also, improvements were made in the surface from the network of curves in terms of smooth connections. Calculation in NURBS surfaces have been optimized. The shell extension algorithm has been improved. Improvements were made in the patch shell operation with G1 connections. Added new features to median shell operation. An algorithm was also implemented for processing self-intersection of an equidistant contour in rotation operation. Diagnostics of phase connections by G1 and G2 was implemented. Now, some details about these changes. A ruled surface can now be built with the following parameters: by curve and direction, by curve and surface, by curve at tangent to surface, by two tangent surfaces. On the left are examples of building a ruled surface by a curve and surface, by curve and tangent to surface. On the right, tangent to two surfaces. Over the past year, the surface of conic section of minimal stress was implemented, as well as tangent to two sets of faces. Ruled and conic surfaces are used in the modeling of complex forms in shipbuilding and aircraft construction, as well as turbomachinery. We continue to improve the quality of surface from the set of curves. A large amount of work has been done on this topic. I will especially note the improvements in the surface in terms of smooth mating at the boundaries. The patch shell operation. Now it is possible to build a patch shell with specified tangency on some boundaries, if other boundaries are not suitable for constructing a Kunz surface. Improvements to the polyhedral surface extension functionality included creating a common edge if the faces overlap when extending, and splicing of divergent edges during extension. Next, median operation. To this functionality, the option of constructing a median shell from non-equidistant pairs of faces has been added. Next, I will talk about plans for the development of surface modeling. One of the most important problems is the fillet surface of non-connected faces with constant and variable radius. Improvements are also planned in creating patches with mates along the border and along an arbitrary set of curves. The development of an operation to combine smoothly joining faces into a single nerves-based face will continue. Activities will continue along the median shell, and finally, it is planned to develop a method for unwrapping a surface of double curvature onto a plane. In the next block, we will consider changes in solid modeling. Since our previous C3D DevCon in solid modeling, changes have been made to fillet and cutting by shell operations. There were also significant improvements in direct modeling and sheet metal modeling. Added the ability to fillet edges with a variable radius along a boundary curve in the fillet operation. In direct modeling, improvements have been made in removing faces while maintaining body topology, removing fillets, moving faces, replacing faces with equidistant ones. A few words about changes in sheet metal modeling. The operation of normalizing holes in sheet metal is used for preliminary preparation of the edge of sheet material in the case of inclined cuts. Added a new way to form an edge when stamping with an arbitrary body when specifying a piercing. There are the basic development plans for solid, direct, and sheet metal modeling. We will continue to improve our direct modeling capabilities. Also, already in development is a new operation to slope the specified faces of the solid relative to edges. In addition, we deal with processing of self-intersection in the kinematic operation. In sheet metal modeling, work will continue on flanging the sheet body and specifying deformable and non-deformable areas for sheet body bands. Now, relatively recently, we began to develop functionality for polygonal modeling, which is becoming more and more popular with our customers every year. Recently, work has been carried out in following areas: calculations of intersection curve of polygonal objects, a Boolean operation on polygonal objects, diagnostics and repair of polygonal objects, added some methods of polygonal object simplification. Ray tracing algorithm has been optimized. The next step is optimization of processing copies of polygonal objects. And finally, the C3D Shaper module, which performs the transformation from a polygonal to boundary representation, is being further developed. A few details for each area. The functionality for calculating the intersection curves of polygonal object has been implemented. The result of this operation will be some set of polyline curves. Already, in the current version of C3D Kernel, it is possible to perform Boolean operations of union, subtraction, and intersection of polygonal objects. You can see the results of the Boolean union and mesh difference on this slide. Diagnostic of polygonal objects. At this stage, an assessment of the closeness of polygonal meshes is implemented, as well as a diagnostic of following defects: the search of boundary edges of the meshes and the check for consistent orientation of the mesh polygons. Also, an algorithm for repair the orientation of the polygons has been implemented. Mesh simplification. Mesh simplification is the process for reducing the number of polygons used in mesh while keeping the overall shape as much as possible. The user can set the desired number of polygons or set the accuracy target value. C3D provides implementations of algorithm for computing 3D convex hull of point sets. In the current version of C3D Kernel, an algorithm for 2D convex hull has been added, as well as improved and optimized the C3D case. At the moment, a new functionality for obtaining a planar projection of a polygonal object is under active development. In this projection algorithm, it will be possible to add various shell objects and polygonal meshes that can affect the visibility of each other. A few words about the C3D shaper component, which is responsible for converting polygonal meshes into boundary representation. As part of the work in this area, segmentation algorithms have been improved, and algorithms enable surface fitting into a set of mesh polygons were improved. And the user has been given ability to control the parameters of recognized surfaces before converting to a boundary representation. The result of such control are presented on the right. After recognition, the parameters of the local coordinate system of the plane, as well as the radius of cylinder, were changed. I will note the main planned direction for the development of polygonal modeling for the near future. By the end of the year, work on the projection of polygonal objects will be completed. It is planned to implement algorithms for calculating an irregular triangulation grid, taking into account the user-specified fixed points. The Boolean operation on polygonal objects continues to be improved. Some mesh repair algorithms will be implemented. And of course, we will pay attention to the development of C3D shaper component. Finally, I will talk about a few activities that I would describe as general kernel work. At the moment, in the process of implementation, the problem of controlling the accuracy of building models. Recently, the projection algorithm was optimized in the case of presence in the view of overlapping identical objects. We have also achieved acceleration of projection algorithm with the option of center line projection. In conclusion, I would like to note that all our plans for the development of C3D kernel are format taken into account the needs of our customers. Thank you for attention. Goodbye.
Wow, that was a beautiful presentation. Thank you, Andrei. Impressive. I'm pleased to announce our next guest speaker, Svetoslav Golovanov, who will share his experience on developing CAD solution based on C3D.
Hi, everyone. I'm Svetoslav Golovanov, and I'm going to tell you how to make a CAD application with the C3D kernel. The key point is that the geometry kernel is the main part in every CAD application. But there is no way to use any geometry kernel directly. Just as an engine needs a car to run it inside, so every geometry kernel needs an application. There is a list of necessary components for a CAD application. Obviously, a geometry kernel, C3D, then rendering engine, a custom tool based on OpenGL, DirectX, Vulkan, or Metal. Also, C3D Toolkit has high-level rendering engine, C3D Vision. The next item, framework for a user interface like .NET or Qt or others. And infrastructure for handy modeling, manipulators, undo, redo tools, some user settings, working modes, and others, and utils. It seems that the entry to CAD world is not so easy and requires much time in developing. But I have a good news. There is the Math3D project that can reduce these requirements. Math3D is a small CAD system which is currently being developed. Already now, the project can be used as a platform for a quick start for solving CAD problems. In addition to the above requirements, the following functions are implemented in the Math3D. Plane sketches and space wires. You can create contours to extrude, revolve, sweep, etc. Make Boolean operations, fillets, chamfers, mirroring, offset of faces, and others. Then Math3D supports modifying and creation of assemblies, move, transform, align, copy, delete operations for parts. Each operation is written to a history. Undo and redo are supported. Also, you can change settings, change tessellation, it means change triangulation, quality of models, change colors, or change attributes, change view modes, etc. You can perform dynamic plane section and make projections of space models to a plane, and direct modeling operations are going to be implemented. There are some pictures that demonstrate the functionality of Math3D. Boolean operations, shell operation give a thickness for a surface or body. Blending faces, creation surfaces through several contours or by contours and a spine curve. Of course, regular and familiar extrusion and revolving operation are also implemented. The next one, building symmetrical bodies. You can create a plane and get symmetrical. Then cutting bodies by a contour or a surface. And there are several tools for assemblies. Replication by pattern, linear or circular. Alignment by axes, planes, or points. And there are some assistant tools for exploring models. Plane sections, calculation of distances, center of gravity, etc. Unfortunately, the website of the Math3D is not working now. The new interactive website is being developed now. But if you are interested in the project, you can send email. And if you have any questions, I'm ready to answer them. Thank you for your attention.
Well, thank you, Sviatoslav. It was nice to hear about your application Math3D. I think that Ekaterina and I wish you success with your application. And now we're inviting our next speaker, Sergey Belov, with his presentation about C3D Solver. It is the second module, but an extremely important one for CAD developers. Sergey, please proceed.
Hello, my name is Sergey Belov. I'm happy to work in the C3D Solver group. And today I would like to tell you about the products that our team is developing. Let's start from the two-dimensional constraint solver. I'll tell you about the two most significant improvements of this year. Two-dimensional solver allows you to create a very complex parametric sketches. For these purposes, we provide a wide range of geometric objects. For example, a line segment, a circle, an ellipse, a spline, a constant parametric curve on which various constraints can be imposed, both logical, such as symmetry, tangency, curvature, equality, as well as dimensional constraints, such as distance and angular dimensions. We also provide constraint system diagnostic tools that allow you to determine which constraints override the system or make it inconsistent, as well as to learn about the presence of degrees of freedom of geometric objects after imposing constraints on them. The geometric dragging tool allows you to manipulate a sketch in a way that changes of the non-manipulated part of the sketch are minimized. We also provide an API call logging tool that makes it much easier for our customers to interact with us, often allowing you to simply send us an API call log instead of a complex and sometimes difficult verbal description of a problem. In addition to the C++ API, we provide to our customers JavaScript and C# interfaces. For parametric modeling, splines are very important curves, in the same way that are very complex objects for analyzing and solving algorithms, since splines can have a large number of control points. The solver supports many constraints with splines that involve control and interpolation points and their parameters. This year, we have worked hard on improving algorithms for tasks with splines with a large number of control points, and we have significantly improved performance for all constraints with such splines. On the slide, there is an example in which the performance increase was up to 100 times. The figure on the right shows a sketch in which a large number of splines, each consisting of more than 100 control points. The second improvement has to do with constraint statuses. Two-dimensional solver assigns a status to each constraint that can be carried by the corresponding function. These status codes provide valuable diagnostic information. They inform the user which parts of the sketch are overdefined or form a redundant subsystem. Thus, a group of constraints that is not involved in over-constraining or other solution problems are marked with the well-treated and well-conditioned statuses. The well-conditioned, ill-conditioned, and redundant statuses together mark a subset of constraints that together form redundant groups or could potentially participate in unresolvable overrides. It should be noted that the well-conditioned status belongs to both the well-resolved part and the set that is supposed to be overdefined. We have significantly improved the analysis and search for redundant constraints by adding new algorithms and improving existing ones. For example, if we take 3 lines and impose 3 parallelism constraints between all pairs of lines, then now the solver detects that it is enough to leave only 2 constraints. Our next product is a 3-dimensional solver. It allows to create parameterized assemblies in which solid components are mated to each other using logical and dimensional constraints. To create such assemblies, we provide a wide range of three-dimensional objects, such as a plane, a line, a circle, a cylinder, a sphere, a cone, or simply a solid body of arbitrary shape, on which you can impose various logical constraints, such as tangency, symmetry, or coincidence, as well as distance and angular dimensional constraints. In addition, it is possible to create arrays of components from objects arranged according to linear, angular, or cylindrical laws. Also, in the three-dimensional solver, there is a functionality for analyzing degrees of freedom, dragging, and logging API calls, which obey the same principle as the similar functionality of the two-dimensional solver. We also provide a C# interface for the three-dimensional solver as well. Another problem that the three-dimensional solver can solve is the construction of parametric wireframes and pipelines. Such frames and pipelines are built using line segments with variable lengths and circular arcs with variable radius and arc lengths. All the constraints that are supported for them can be applied to these objects, such as coincident, parallel, perpendicular, tangent, linear, and angular dimension. Also, when constructing wireframes and pipelines, the other functionality of the three-dimensional solver is fully available. This is the analysis of degrees of freedom, dragging and logging of API calls, and C# interface. A framework model differs from an assembly solid models in that the constraint mated geometry of a framework is specified in a common coordinate system, while the geometry of an assembly belongs to the solids that are part of the assembly. Also, when dragging, the three-dimensional solver takes into account that it is dealing with wireframe elements and sets up rules of behavior that are connected with the specifics of wireframe models. Let's move on to the main novelty of this year. This is a distance interval dimension. A distance interval dimension allows you to set valid bounds for some dimension within a certain range. This dimension can be defined both between different solid parts and geometric entities of the same solid. Valid interval dimension values are the same as valid values for a similar driving dimension. It allows a smooth switch between driving and interval dimensions if required by the client application. To declare the distance interval dimension, we have added the GCM interval structure as seen on the slide. To apply a distance interval dimension constraint, use the GCM at distance function, which is an overload of a similar function for creating a driving dimension. And now I want to talk about another product that our group is developing. It's a collision detector. The main task of this module is to search intersections between objects of a geometric scene and instances of the same object quickly. Collisions can be searched for solid bodies in the boundary representation, polygonal models, and also arrays. You can create your own carries for the detector and customize them using the callback functions. Also, the detector allows you to determine the minimum distance between parts of the scene. The main advantages of this module are as follows. First of all, its performance. Geometric search algorithms are optimized for real-time search. In carries, you can configure between which parts of the scenes to search collisions. The algorithms are memory optimized. All objects are stored in a compressed representation, and the same object can be reused as an instances. The first novelty of this year is the ability to add arrays to the geometric scene. In our understanding, array is a geometric array that has an origin and a direction. The detector processes carries to search for intersection of array and a solid or a polygonal model. The check collision function now also works for arrays and detects the intersection of array and the solid as well as the intersection of arrays between themselves. To add array to the detector, you need to use the addArray function, which takes the coordinates of the origin of the array, the direction, and the transition matrix to the global coordinate system. Also, this year, we received requests from our customers for the possibility of detecting that one body is entirely inside another. It is especially important for the construction industry. We have made this possible. If one body is completely inside another, then the detector will now report a CDET included message. You use the CDET included message in the callback function to customize the behavior of the detector. In addition, we have implemented a C# collision detector API wrapper that completely supports the C++ API, including callback functions. All standard C++ carries to the detector are also wrapped. But more, you can create your own carries in C# and use your arbitrary callback functions with C# types for this. On the right, there is an example of using such a callback function. And here is an example of how to declare a callback function in terms of C# and then create your own carry for this function. Thus, now all of our products, two-dimensional solver, three-dimensional solver, and collision detector have a C# interface. And a little about our plans for the near future. In the next year, we plan to implement linear and angular patterns in the two-dimensional solver and affine patterns in the three-dimensional solver. We plan to add angular interval dimensions to the three-dimensional solver and distance interval dimensions to the two-dimensional solver. We will also develop the functionality of splines and improve the algorithms for working with them. We will continue to improve the tools for analyzing the system of constraints. For the collision detector, we will develop a new API in the style of the C3D Solver. In addition, we will continue to develop the functionality of the detector. In particular, we plan to add accuracy control and new detection cases, various options for objects touching each other. You can find out about our long-term plans in our roadmap. Thank you for your attention, and here is my contacts.
Thank you, Sergey. Good job. Dear participants, please don't forget to ask your questions in our chat to Sergey and other speakers. And now get ready for Nanosoft presentation. Alexey Fedorov, our guest speaker, will tell us about C3D Solver and how they use it for Nanocad development. Alexey, please start.
Hello, my name is Alexey Fedorov, and I'm going to tell you about our experience of using C3D solvers in the 3D module of the Nanocad application. It's a product of Nanosoft company. It's a CAD application, primarily targeted for Russian market. It has a familiar AutoCAD-like interface, powerful drafting and design tools, native DWG compatibility, an open API for C++ and .NET, and it has a built-in 3D module currently working on C3D modeling core. This is a typical screenshot of Nanocad. In this particular picture, a 3D modeling sample is demonstrated. Several years ago, Magma Computer, the company I work for, started connecting a 2D constraint solver to Nanocad. The task came from Nanosoft company. Initially, it was 2D solver from Ledos company. Then we did the same job for the 2D constraint solver from C3D. And finally, we've attached its 3D constraint solver. Currently, solvers are connected to Nanocad in three ways: a DWG model, a direct connection of 2D solver, and direct connection of 3D solver. Now let's look at these ways a bit closer. The first one is a DWG model. It consists of 4 layers. The first one is the main application itself. The next is the layer of the ODA SDK. Then there is a specific 2D constraint solver. And the last one layer is the 2D solver itself. It's designed so every layer may interact with 2 layers only, the one above and the one below. It's displayed with blue arrows here. A constraint solver cannot interact with the main application. On the whole, it causes a set of functionality limitations and performance issues. In order to avoid some of them, Nanocad directly interacts with all mentioned layers. It's displayed with pink arrows. The next attachment scheme is a direct connection of 2D solver. In this case, the DWG layer is completely excluded. Nanocad uses such type of connection for solving flat parametric sketches in standard 3D parts, objects in database, such as nuts, flanges, and so on. In this model, a 2D constraint solver is connected through a small gate module, which is implemented as a C++ library. Nanocad may almost directly interact with the solver. The last connection scheme is a direct connection of a 3D constraint solver. Nanocad uses this model for evaluation of constraints between 3D parts and assemblies. Now let's look at the 2D constraint solving process itself. In a DWG model, it may be represented by 3 stages. The first one is an event telling us about changes in object's geometry. The stage 2, identifying the type of such changes. And the third stage is constraint system solving in a certain way. Simple shifting of an object, simple rotation of an object, moving a vertex of an object, and general solving. A question may arise here, why we need to determine a type of geometry changes. It seems it's something that should be known by definition. If a user moves the whole line segment, it should be a simple shifting mode. If he moves the ending of a curve, it should be a vertex movement mode. However, in a DWG solver connection model, changes are initiated on the top level, a level of application. But a solver is isolated from the application by abstract and common purpose interfaces. Now I'd like to demonstrate just mentioned calculation modes. The first one is the simple shifting of an object. On this screen, the most left green line is about to be shifted upward. Here is the result of calculation, sort of animation. We may see that the shifted line is at the user desired placement. Other objects retained their relative position, but got a slight rotation. But this isn't an error because the rotation of objects isn't limited. Now let's look how simple rotation of an object is processed. The blue line at the bottom is about to be turned to a position of the yellow line. So its lower point must remain fixed. Let's look at the result. Again, sort of animation. And we may see that the line has been rotated correctly. And the rest of the sketch has been properly repositioned too. However, there are questions to the left line with the ending without any constraints. We may see that the line has been rotated so that its length remains the same, and as if an angle with the adjacent vertical line was fixed. Another possible way to recalculate for this line would be to keep the left ending on its place. Nevertheless, the constraint system stays in a correct state that satisfies all existing constraints. If a user requires more predictable behavior of calculation, he should provide additional constraints. This is the most helpful advice for such cases. On the next screen, the ending vertex of the green spline is about to be moved to the pointed place. At the same ending, there is a smooth constraint that's set between the spline and the red line. Smooth means G0, G1, and G2 curves connection. And here is the result of calculation. To unknown reason, the solver has rejected the target position and has calculated the system for another point, this one. Additionally, the spline got a noticeable excessive curvature, though all constraints here are in a solved state. I guess there is a bug in gate modules for a solver, and this is the issue for further explorations. Finally, let's look at the general type of constraint solving. Its purpose is to bring a constraint system to a state when all constraints are satisfied. Such way is suitable, for instance, for the case when parametric constraint values are changed. In our sample, a user has entered new values for all three parameters of the sketch, values for radius, distance, and an angle. Here is the result. 3 pointed geometry entities have retained their positions. We may see that the geometry of the sketch looks similarly to the initial one, and objects' relative positions have also been kept. Everything looks fine. Now, some words about the direct type of connection of 2D constraint solver to Nanocad. Such model is used for calculation of 3D standard parametric paths, templates for which are stored in a database. On this particular screen, we may see a model of the node. The image in the left bottom corner is the 3D modeling history tree. The sketch with constraints in the center of the slide participates in this model calculation. The important point here is that the sketch must be fully constrained. Such condition eliminates all issues relating to calculations of under-constrained systems. Today, the 2D solver is successfully connected to the Nanocad application and carries out all required tasks. However, things weren't so fine when we started working with it. Some issues took place and had to be fixed. Some of them were significant, were simple but significant. Fixing others took more than a year. The current slide has a list of such solved issues, and I'd like to talk a bit about them. Let's start from the one that was successfully solved with an assistance of the C3D Labs team, but without changes in the solver's API. Some consultations took place. Then we managed to implement a symmetry constraint for C3D Solver. The point is that the C3D Solver requires a programmer to specify every aspect of symmetry explicitly. The symmetry for points, arcs, ellipses. There is a specific processing for symmetry even between boundary lines and their unbounded versions. Looks quite complex, but finally it works. Rigid sets in 2D constraint system. Initially, 2D Solver in C3D didn't have API to create such objects. A rigid set is a set of geometric primitives that are fixed relatively to each other. In a DWG model, such sets are required for applying constraints between instances of block references. On this current picture, you may see two rectangles. Some constraints are applied to them. In this case, 4 lines in every rectangle are composed into a single rigid set. So we have 2 of them. C3D Labs implemented the required functionality in response on our request. These 3 functions were added to the API of the solver. Lots of work was done for implementation of a smooth constraint. Smooth in terms of TWG is a composite limitation representing a G0, G1, G2 connection. In other words, equality for point coordinates, tangents, and curvature. The scheme on the screen contains the set of implicit constraints and their relations required for representing such a complex object. During our discussions with C3D team, it was decided to implement API suitable to calculate the same structure of limitations as the displayed one. Names of structures and objects are slightly different, however, their meaning is similar to the ones in the DWG model. The last significant improvement in the API of 3D Solver relates to the generated values of parametric constraints. It's irreplaceable in case when you need to create different implementations of 3D parts using the same 3D model. The NAT object displayed on the left has two implementation. The top one has chamfers, shown in green color, and the bottom implementation doesn't have them. This sample is provided only for understanding the discussing topic. Of course, real NATs always have chamfers. With new improvements in a solver, we may inform the system that dimensions N4 and D6 in this case may degenerate to 0. Then we put such values into parameters, I mean zeros, and execute a general solving. The last part of my presentation, I'd like to tell you about how we've connected a 3D solver. Currently, an Nanocad application offers a user 6 types of 3D constraints: a fixation, a mating, an angular constraint, an insert, tangent, and asymmetry. This set provides the minimum necessary constraint types for 3D assemblies modeling. The table has information about types of object geometry references that may be put together for every type of constraint. The mating constraint is the most functional one. It may be used for mating any pair of such primitives as a point, line, and a plane. There are 9 combinations to take into account in order of constraining objects. I mean that, for example, a line plane and plane line relations are different in this case. Talking about the tangent constraint, not all possible combinations are currently valid. For example, a cylinder surface cannot be used in a pair with the conical or spherical one. Moreover, a tangency between two cylindrical surfaces doesn't mean that their axes will be parallel. Such limitations must be added by users explicitly. Some items of 3D body may participate in different 3D constraint relations. The most representative one is a circular edge. It may be represented as a point, the center of an arc, as a line, the axis of an arc, and as a plane that the arc lays in. Nanocad interacts with the C3D Solver directly using the scheme that's displayed on the current slide. The initial step is to collect a set of altered 3D bodies. Then, when the update event comes, the calculation of 3D constraints begins. It carries out into 2 stages. First, a fixation is applied to all 3D parts that were moved. Then Nanocad queries a 3D solver to calculate constraint system. If it's successful, the result is applied to a model. If the stage fails, a general calculation of 3D constraints system is applied. If this stage fails too, Nanocad collects states of every 3D constraint using the information provided by the solver. Such states as solved, conflicting, excessive, and so on. Then this information is reported to a user. Here is an example of such case. There are 3 constraints. They are applied to a couple of cylinders. 2 of constraints are inconsistent. The angle constraint and the cylinder's axis mating. In this sample, a user has just entered new value for an angle. The valid value is 0, but now it's 155, and it conflicts with the existing mate constraint. The effect of inconsistent is visible to a user, so he may fix corresponding errors. So that's all for technical details. Let's make a little summary relating to C3D Solver's 2D version. Supports all 2D constraints required for DWG format, predictably solves fully constrained 2D sketches, has acceptable calculation speed, has better functioning and performance in direct interaction. 3D version of Solver has a user-friendly, understandable API. It's robust and qualitative, no issues found so far. And I should state that both solvers don't require special license. The general one enables all of them. I hope my story was interesting to you. We appreciate C3D Labs for their professional assistance. I believe the job they've done for us made a positive contribution to the C3D product itself. That's it. Thank you for your attention.
Thank you, Alexey. Nanosoft, you guys rock.
Now we'd like to take a break for a little and hold an award ceremony. Every year we reward our customer who make the greatest contribution to the C3D Toolkit development. How do we determine the winner? We pay attention to some criteria. How many support requests do we receive from him? How difficult are these requests? And how do they help us move into new areas of modeling development? And this year the award goes to
Nick Kalin, the creator of the Plasticity product. Nick has sent us almost 150 questions and requests, and that seems to be a record. Thanks to his effort, we have made significant progress in the development of direct modeling functionality.
Thank you, Nick. We appreciate your contribution to our development. By the way, be active users of C3D, and next year we will reward you.
Okay, so let's move to the next part of our conference. And our next speaker is Alexander Spivakov. He will talk about C3D Converter and how to solve customer tasks with it.
Hi, colleagues. I am Alexander Spivakov, the lead of the C3D Converter team. Now I'm going to present the changes which happened to the product for a year. Before speaking about changes, I'll have a couple of words about the converter itself. Then, after the functionality update is shown, our plans for the future will be discussed. Have a look at the position C3D Converter has in the toolkit. First, it should provide all other components with high-quality models created beyond the C3D ecosystem. Second, export 3D models for using them in applications which are not based on C3D. So C3D Converter reads and writes shapes presented in forms from solids and meshes to points, also attributes manufacturing information. Physically, files, memory buffers, or special API files are available. Now let's have a look at new features. Since our API seems to be the most conservative, read and write, new methods are usually is an event. Okay, if principles of shape description are more or less equal in different applications, the rules of attributes naming may vary, and it seems that there is no regular way of matching them on input. So to solve this mismatching as soon as possible and as fast as possible, a special way of input was implemented, preliminary input. In this mode, we just scan the source and give a list of names of attributes to callback function, which should be implemented on the side for the end user applications. First, Callback should be given to a converter for registering, and then preliminary import should start. Unlike reading these suppressed shape filters, it may be kind of side away. It doesn't create any model, so there is no need to implement and give us any mock model document. The next API change relates to export into step files. Since step files have 8-bit encoding, but applications can be Unicode-based, losses on conversion are possible. There are two main ways how to prevent them. Use special step notation for Unicode symbols, or make sure both applications use them encoding. But if the first way is chosen, some applications or step processors may read the encoded strings as is without decoding. Now there is an opportunity to change the text representation in runtime. If it turns out that third-party application does not read correctly saved step files. 3 predefined applications implementations are available in the box now. Step notation, locale-based, and obvious UTF-8. Now, let's have a look how we improve the work of converters. Here, there is one point of concerning API. We updated design of plugins API to provide binary compatibility of several versions without changes to the application code. Other improvements are related to Polygon converters, attributes management, and our traditional work, keeping supported forms up to date. Usually, Absolutes used to be the main source of meshes to export, but it changed when we had to export models from STL to JT. The encoding algorithms of JT format are as efficient as sensitive to mesh data. We managed to find a way how to export grids containing several normals at one vertex and not inflate target files. Our traditional focus is keeping supported forms up to date. There is nothing unusual in these figures, as should be. Anyway, we did not used to support SS version 27 and Parasolid version 30 on even 31. Sorry. The first implementation of plugin API was object-oriented, and for that reason, we managed to get MVP quite soon. We expected it would be quite difficult to add new features to that API and design plan a C API. It doesn't look so elegant, but much more open for modifications. Here is a bunny imported from, if my memory serves me right, AMF format. We didn't have to change the test application, just a plugin. The next challenge we got from customers who plan to work with the library for PNG format support. The library used some open source libraries, and some of them were the same as C3D. And the binary interfaces turned out to be the same. So they couldn't build the application because the linker couldn't decide which one to use. On our side, we changed the compiler options and some markers to hide the third-party entry points, and so resolve the conflict. In future, we're not going to stop our traditional work, provide and improve quality of translation. And as for API changes, we're going to make it as simple as possible. And for that reason, we're going to decrease the number of methods without, of course, losses of functionality. And regardless of our plans, we're open to new cases. Before leaving you, I would like to answer one question in advance. We don't consider support create formats as functionality of mathematical kernel. C3D Converter is open for integration with other products. Thank you for your attention. Hope to see you next year. If you have questions, feel free to ask me.
Thank you, Alexander. It was nice to know about the new abilities of Converter. Next, I want to invite our guest speaker, Leonid Karlstein. He will tell us about how C3D Labs solutions are used in past software. Leonid, we wait for you to join us.
Hello, everybody. I'm Leonid Karlstein, VP of Research and Development and Piping System Research and Engineering company. And I'm happy to participate in this event. And first of all, I would like to express my my pleasure to participate in for invitation to our partners C3D. And I would like to tell you about our joint experience of usage C3D Kernel in our software products. But first of all, several words about our company. So our development team has more than 50 years history. First in different industry institutes, and then as a separate private firm company. And the software already have more than 3,000 active users. And the key focus of this software is engineering analysis for piping, plant, industrial safety. And we try to use in our software the best-in-class modern methods, algorithms, and libraries, and embedded knowledge from industry experts in combination with user-friendly interface and flexible licensing and CAD integration. On international market, we are known under the brand PAS. So in our group of companies, we have three companies. Piping System Research and Engineering, which is concentrated on software development, engineering and industrial safety, piping and equipment non-destructive diagnostic, and also applied scientific research, which are necessary to develop these activities. We also have our design company, which uses the same software as we develop and design different facilities, mostly in refining and petrochemical industries. And we also have our training center for offline and online training for our software and also some partner software. About our PAS software. It includes everything that is necessary for piping and equipment analysis, both fluid flow analysis and heat exchange analysis, and stress and stability analysis. And include 4 programs. So it's Hydro System for fluid flow, Start Pro for piping stress analysis, PAS Equip for equipment stress analysis, pressure vessels, columns, tanks, heat exchangers, and also PAS Nozzle FM for nozzle shell junction stress and stability analysis. It's more than 50 years on the market, but on the international market, we actively started only on 2018, but now we already are very active in many countries. You can see this on this map. So we have users on all continents. Now about our interaction with C3D. P3 has licensed C3D in 2013, and it was one of the first C3D users. And C3D is now used in our PAS Equip and PAS Nozzle FM software, where it replaced our obsolete 3D kernel. And this is natural because in this software we need to model the most complex geometry for different pressure vessels, nozzle shell junctions, and we use it for modeling complex pressure vessels, for mesh creation, for volume and mass properties calculation, and also to export our models to different CAD formats for transferring to different CAD software. This is done using C3D Modeler and C3D Converter. Now about this software itself. So PathEquip is an analysis software for strength and stability calculation for horizontal, vertical, column pressure vessels, tanks, and different types of heat exchangers. And it contains a vast database of typical elements and materials, and provide different features for CAD integration. Here you can see some of our customers worldwide in oil, refining, chemical, petrochemical, oil and gas, thermal power, and other industries, which include European customers, South Korean customers, many American, many others. I'm sure you can find some companies which you, of course, know. So we have different national codes, international codes as ISME, European codes, API 650 for tanks, and some others, including large material database holding different codes, ASME, European, Chinese, and so on. And the philosophy is what you see is what you calculated. So you just see all details of our models with all internal structure, with all elements, with all structural elements, just in the model. And you can look at it in wireframe, in solid, in transparent view. What is more convenient for you? Well, like this, for example, you see all internal structure of these heat exchangers. There's some examples for model expert. For example, this is complex pressure vessel, and here is this model is exported into AutoCAD, and this is examples of exported of PathEquip heat exchanger model into AutoCAD. Into SolidWorks using C3D Converter, and for example, here you can see that we have all details, and we can create some sections of the exported model in SolidWorks. There are some tools which we have. For example, for heat exchangers, we have a very powerful tool of tube sheet editing. We can define any complex tube sheet, and you will have just exact 3D representation of this tube sheet. We can define vertical tanks with all the elements, heads, nozzles, ladders, and so on. Structural detailing, foundation. And here some complex examples, nozzles on the nozzles, different type of nozzles, different type of supports. You can see different types of heat exchangers, complex equipment with several equipment pieces connected, columns with all structural elements, platforms, supports, and so on. And separately, there is a very interesting Path Nozzle FAM software, which is a special tool for solving problem with nozzle shell junctions, because it's necessary to quickly analyze them, to get allowable loads, to get stiffness flexibility for this junction, stress intensification factor, to make fatigue analysis. And this is only possible for, in general, by finite element method. So this tool provides a very easy way for ordinary engineer to do this. So all you need to do is just define geometry. What is your shell? What is your nozzle? How it's they are connected, and everything can be done automatically, including mesh generation, and you can control quality of the mesh automatically or manually. The analysis takes several minutes, and you immediately can look at everything in this nice post-processor, including all stresses, different components of stresses, the different combination of loads, and so on, and fully understand what's happening. And here are some more complex examples with interaction of several nozzles, or with flat box nozzle junctions, or with connection with several shells with different temperature. And here are the thermal stresses. And this pass nozzle FAM is also integrated both with pass equip, so you can immediately get all data of all nozzles of your vessel and analyze them. And you can also have two-side integration with our piping stress analysis software. So you can analyze any nozzles or any non-standard elements in the pipe, and the flexibility, the level of loads can automatically be returned in your piping stress analysis software. So all this, of course, can be done due to very effective use of C3D Kernel for geometry modeling and for model conversion. Thank you, and I'm ready to answer your questions.
Thank you so much, Leonid. That was real expert talk, and of course we are wishing you success with your past product. And now I'm inviting my co-host and colleague Artem Maximenko to tell us about Web Vision. It's a brand new solution for web visualization. I hope you, Artem, are prepared and ready to start.
Hello again. So I'd like to take a break from leading this conference for a little and tell you about new functionality which we implemented in our web visualization module, C3D Web Vision. But before moving on to report about new tools of this component, I'll talk about our desktop visualization products, because today I will mention and compare Web Vision with them. Here you can see the agenda of my presentation. As I said, I will start with our desktop components, then move on to new tools of Web Vision and its integration scheme. Finally, I will show a short video and talk about our future plans. Well, C3D Vision is a desktop cross-platform visualization. It's written in C++, it runs using OpenGL on Windows and Linux operating systems. Vision includes two libraries to integrate it with your app, the MFC Vision and Qt Vision. The latter simplifies your integration with Qt to a minimum. There are also a C# wrapper for Vision that allows you to use our visualization with C# code in your application. C3D Viewer is a cross-platform and application. We developed the viewer to demonstrate how all our components work together. So it uses C3D Vision to visualize, C3D Modeler to generate meshes, and C3D Converter to read third-party formats. The graphical user interface is implemented using Qt. Viewer has an ActiveX API for Windows only, and so this can be embedded into third-party products. Last year, we announced web visualization. Our main goal was to achieve the same functionalities of the desktop visualization C3D Vision. These are functionalities such as dynamic sections, annotations, rendering modes, and much more of what Vision provides. That's why we implemented C3D Web Vision using our desktop visualization and its sources converted with Emscripten. To render 3D graphics, we use WebGL instead of OpenGL. To load models, we use REST API on the backend side. Now let's talk about new tools which we implemented just last year. First of all, we added the ability to switch between several rendering modes of models: wireframe, shaded, and shaded with wireframe. We plan to add more modes later, such as hidden edges and model outlines. By the way, these modes are available in the desktop visualization initially. We brought one of the new abilities to Web Vision only. It means it's not available for desktop vision. The ability lets you colorize model segments, so you can select certain elements and set a color scheme for them. Web Vision loads schemas when it's loading, so you have to specify which color schemas you need to use, but you can change them while Web Vision runs. We also made some changes to camera processes. Last year, we presented Web Vision 2021, and showed its functionality related to the camera, zoom to fit, standard rotations, but now we extended these functions with camera annotation abilities. By comparison, the desktop vision has an animation mechanism implemented inside, and animation works on the principle of blocking a thread. So if we call the animation, then vision blocks the thread and then renders a frame. But such an implementation doesn't work on the web, as it requires to implement rendering in a certain frame of a browser. Therefore, we had to move all animation functions from vision to a TypeScript level, and now each frame is rendered in a browser animation frame. To keep track of animation stop, the command which starts animation returns a promise. So this allowed us to add the ability to interrupt animation on the web. It means the following. When we switch to a different model view, the current animation of switching, if running, will be interrupted, and the next animation will be started. We added another new function for Web Vision only, which lets you to get camera parameters. This can be used to implement view customization. The camera has the following parameters: a position in space, 3 coordinates, an up vector, and animation duration. You can see the video now. Let's wait till the animation starts again. Here we can press the Save View button to save the current view, switch to another orientation, and then press Reset View to smoothly return to the camera view which we saved. Annotations. Annotations are a very important geometry in visualization. Previously, we had some issues preventing an implementation of rendering text on the web. One of these issues was related to loading fonts. By comparison, there are no such issues with desktop vision, because we know where to get text fonts. Windows has a registry, Linux has special configs, etc. However, this doesn't work for a browser. Fonts must be loaded at first, then correctly converted to a visual format. Therefore, we took the approach used in Vision. That means creating a font using free type, and applied this approach in Web Vision. In addition, we added the ability to load fonts to Web Vision when it initializes, so you can select fonts you need and use them to render. By the way, I should mention that we also decided to completely change the text visualization mechanism in Web Vision. We developed a new object, geometric annotation, and even improved its performance compared to the desktop vision. Pay attention to the slide. You can see how the texts are rendered in a perspective projection. The right animation shows texts which have different font sizes, depending on how far any of them are from the observer. But the left animation shows texts which have the same font sizes, regardless of their location. Also, we have the ability to add custom annotations with the annotation object. Returning to the issues I mentioned before, it's worth mentioning one more. We consider that Web Vision model, which we read, is read-only, so we cannot change this. However, there is often a need, for example, to display annotations in the model, dimensions, etc. Therefore, we added a special client-side model to the client side. It has two functions, add annotation and delete annotation, for adding and deleting annotations respectively. So you have the ability to add two types of annotation objects to the model, a linear dimension and a comment. The image on the right, by the way, shows the same comment in JSON representation. Processes. A process is a mechanism that allows you to control the model. For example, change the camera position, highlight and select objects, manage dynamic sections, and much more. One of the main processes is geometry search. We came to the conclusion that desktop vision has the geometry search mechanism, which is not quite suitable for us. Its performance and functionality are not enough for the web. It highly depends on rendering and requires enabled OpenGL context to work. Therefore, we moved away from dependence on GL functions in Web Vision. This in turn made it possible to implement such functionality as a deep search. Now we can find all the objects that the cursor crosses. I should also note that we implemented several types of geometry search. The first type is picking, when the object is searched under the cursor. The second type is search using two frames. The cutting frame lets you select objects when they completely are in the frame, and the unifying frame lets you select objects when it only intersects them. As I said before, there are two processes to work with annotations. Now you can use comments and linear dimensions. So the animation shows the process of placing two comments. These processes add annotation geometry to the front side using interactive input. Also, we plan to implement measurement processes. We implemented the processes for adding and editing dynamic sections. To add a dynamic section, you should define a plane by specifying 3 points on geometry. Please pay attention to the animation. It demonstrates loading a model with 19,000 elements, such a rather small model with 1.5 million triangles. Now we can see how it's loading, and then we can create a plane with the 3 points on the geometry, and then we can edit this plane manually. In the meantime, we haven't implemented the process of editing sections using manipulators on the web. I propose to see how it works on the desktop. The animation demonstrates editing a section using a manipulator in the C3D viewer. The same interaction will be available in the next version of Web Vision. Next, before I move on to what's new on the backend side, I'd like to talk about how C3D Web Vision generally works. So let me show you a scheme that reflects the structure of our web component. It's a complete web-based solution for visualizing 3D models, similar to API of C3D Viewer ActiveX. Viewer goes as framework for the structure, so there are the same components which are included into the desktop viewer. To use C3D Vision abilities in a browser, we built its code base with a scripting tool. To deploy our solution on the server side, we decided to focus on a microservice architecture. And that's why we developed C3D Service, which combined the works done by Modeler and Converter components. The geometric data structures are transferred through our own protocol to avoid conflicts with user data. The service has REST API to manage a model. You can easily generate server stubs and client SDKs for different programming languages. It became possible as our API is defined with OpenAPI service, formerly known as Swagger. The client side is a TypeScript that adds a canvas element to HTML user page. The client is managed with TypeScript API. There's a channel between the client and server sides, designed for transferring visualization data. Well, now let's see in more detail how a model is loaded for rendering. Let's consider some storage where the model is located. We know about the storage because we get some information about it from a user. For example, we got such a storage, we need to open the model of such a format, JT, C3D, etc. When the C3D service receives a request to open the model, it tries to get visual data from a cache. If there is no such data, then it goes to the storage, takes the model, and forms some caches. By the way, we use the cache in order to get rid of loading and converting the model into a visual representation, because this process can take a long time. Then the service sends graphics data to a web client. And now let's assume that we have a complex source graphic model, which is not supported by our converters. For example, the model of IFC format. We also need to send attribute information to some database at the conversion stage. The question immediately arises, how the scheme will change with that we don't work with different attributes, because it's not geometry to be rendered. There is a solution. We developed an API, so while a model is read, this allows to separate data depending on what they refer to. It sends geometry to our service to generate a graphical representation, and it sends attributes which we don't process to a database. After reading, based on received identifiers, it forms a model structure, which is then sent to the service as the final assembly for rendering. And that's what it looks like. On the left image, you can see an example of a request to build a geometry. This is a JSON file with geometric data. And on the right image, you can see an example of a JSON model structure. It contains geometry. Finally, I'd like to demonstrate the performance of our web engine. I think this is a very interesting and important point. Now you can see how some model is loading. 22,000 elements, 22 million triangles. In fact, it's a small model. As it keeps loading, it will be possible to see how many elements this consists of. So we can see how this model is loading, and we can see how many elements inside of this. Here we can see doors, handles of doors, the bathroom. Now we will see a kitchen with tiles on the wall. And now the windows are loaded and we can see it anymore. Okay, this model is almost loaded and we can rotate it to see how fast this model is rotated. By the way, it's a very interesting model. We used it to test geometry selection. And recently we implemented rendering of geometry with instances, thanks to which we received a very large increase in performance. So the model is completely loaded and we can switch visibility of some elements like roofs to see what's inside. And here we can see the doors and handles of these doors. We can highlight and select each element of these handles. And it's perfect, as you know. But now we can see a hole, a large hole and a large lamp in this hole that consists of many elements, and we can highlight and select each of them. I think it's rather cool, you know. Okay, returning to instance geometry, I believe that we can improve the performance of rendering, which you can see. We even profiled this assembly and found at least 3 places where we can speed up both model loading and performance. So let's keep moving. Finally, I want to share our plans for the next year. We want to implement embodiments, loading PMI from source model. Also, as I said, we want add manipulators to Web Vision to finally edit dynamic sections. And also we want to add measurement processes, textures, pencil, dynamic font loading. Also, we want to move from WebGL 1.0 to 2.0. And finally, we want to implement camera processes. For example, walk around the model. So my presentation is over. Here are my contacts, and thank you for attention.
Thank you, Artem. That was a great presentation, amazing graphics, and whole Vision team, thank you so much for your hard work. And now we are inviting our next speaker. Tatiana Mitina will tell us about our kernel API. How do we support our stability and compatibility? Tatiana, please join us and proceed.
Hello, colleagues. All components of our C3D Toolkit offer API to access their functions in engineering applications. As a software vendor, we are constantly updating our toolkit with new interfaces. At the same time, we are constantly working to make C3D API completely predictable for users. Today, I will talk about general requirements for API development, the considerations we take into account when developing C3D Kernel API, and how we ensure the backward compatibility of our API and maintain its stability. First, let's talk about API requirements. Customers of API developers are other developers who use the API to create their own software products. API users work in different environments and solve different tasks. Products developed using the API have their own life cycles and release plans. Therefore, API should meet the following basic requirements. API should support different development platforms. The figure shows the logos of some operating systems and compilers supported by C3D Kernel. API should be consistent. It should have the clear structure, consistent naming, and so on, and intuitive, so that the user can start using the new interface by analogy with the other interfaces known to him. And API should develop dynamically. At the same time, it should remain reliable, should be consistent, stable, and backward compatible. Considering the above requirements, when developing C3D Kernel API, we strive to adhere to the following principles. API design should allow developing and extending interfaces without changing existing API. Extending of interfaces should not break the stability and compatibility with previous versions of the API. Ownership of objects created by an interface should be unambiguous. It's good practice to use smart pointers for that. When designing an interface function, it's better to avoid a long list of parameters, which is difficult to manage. Semantic blocks of parameters should be placed in separate structures. When developing and extending our interfaces, we should keep them stable and backward compatible. Let's look at the real example that demonstrates how we are developing new interfaces of C3D kernel. The screenshot below shows the 3 deprecated functions that were firmly used to construct a fillet solid in different ways. And the above screenshot shows the new fillet solids interface created to replace the deprecated 3. In the new interface, the list of parameters has become shorter. The construction parameters are encapsulated in a special data structure. The new interface employs smart pointers, and we can extend this interface without changing it. Next, I will show how this can be done. Let's look at the class of fillet construction parameters. The class provides a special constructor for each fillet construction method. It employs smart pointers, and the class provides the ability to extend functionality of building fillets without violating the stability and backward compatibility of the interface. How it can be done? We can add a new method for creating a fillet solid by defining a new constructor in the class of parameters. This will not break the stability of the interface. We also can extend the existing methods of fillet solid creation by introducing additional parameters and the function for the initialization. For example, we can add control over the accuracy of the calculations to the existing construction methods by adding new accuracy parameters. On the one hand, users will be able to use the interface as before because nothing changes for them in terms of compatibility. On the other hand, users can start using the new parameters. Now let's take a close look at the 2 concepts mentioned above, stability and backward compatibility, what they mean for API development. Stability implies that API should remain unchanged for as long period of time as possible. At the same time, if there is a need to modify an interface, there is a clear procedure for replacing it with a new interface that primarily should maintain the API usability. Backward compatibility implies that the code written for the previous version of the API functionally works in the same way with the next version of the API. Support of stability and backward compatibility of C3D kernel interfaces implies that, first, within one major C3D kernel version, no significant changes are made to the existing interfaces. This means that updating C3D kernel to a new revision does not break compilation of users' products, and the stability of the API behavior is ensured. Any significant API changes are allowed in the next major version. If it's necessary, an interface can be declared deprecated with an indication of its expiration time and the interface in place replacing it. Following the specified period of time, the deprecated API ceases to be stable and can be deleted at any time. To ensure the stability and compatibility of our interfaces, we adhere to follow rules when changing C3D kernel API. An interface cannot be moved or renamed without providing backward compatible aliases. The rule applies for all interfaces, functions, classes, enumerations, public constants. It's not allowed to change the calling conversion, the number of parameters, or their types in an interface function. The sole exception is that a new parameter can be added to the end of the parameter list with a mandatory indication of its default value. It's not allowed to delete, move, or change public fields in interface structures. A new field can be added to interface structure, but only to the end of the fields list. In enumeration, a new value also can be added only to the end of values list. C3D API is developing dynamically. What we take into account when extending or changing the API to maintain its stability and backward compatibility. New interfaces can be added as needed without disrupting existing ones. Adding a new interface should not change the meaning and behavior of existing interfaces. If it's necessary to make changes to an interface function or a method of an interface class, the function is declared deprecated and a new function or a method with necessary properties is added. There are few exceptions to the above rules. Backward compatibility and stability of an interface can be broken without declaring it deprecated if a critical error makes it unusable. Interfaces under development are marked in the comments as experimental and are not required to comply with the stability requirements. For the convenience of our users, we provide information about the API changes in the following ways. The API changes are described in the file changes of the corresponding C3D kernel release. Interfaces under development are marked as experimental in comments. They can be unstable. An interface to be deleted is marked as deprecated with an indication of its expiration date in the interface replacing it. This information is indicated in the message during compilation, as it's shown in the screenshot. Thus, we always strive to provide our users with intuitive and user-friendly programming interfaces, the stability and compatibility of which our users can be sure of. Thank you for the attention.
Well, thank you, Tatiana. I think that supporting stability and compatibility of API is a very important task. So the main part of the conference is complete and we are ready to move to the final stage. So as I said before, our colleagues will show you how to use our components you will see two workshops. One is about C3D Modeler and the other one is about C3D Converter.
So let me introduce the workshop speakers. Artem Avarov will, with his presentation of C3D Modeler, and Ksenia Prokofyeva with her demo of C3D Converter. Artem will start.
Good day. I'm glad to welcome you at C3D Modeler workshop. My name is Artem Uvarov, and I am a mathematical programmer at C3D Labs. Today I'm going to show you some methods of our mathematical kernel and how to use its functionality quickly and simply. I will use a test application to demonstrate the capabilities of the kernel and display three-dimensional models. App was developed by our company. You can see the app interface on the screen now. In this application, you can work with C3D files. It allows you to open, save, and edit the contents of such files. When you open a C3D file, the app creates work window class object. It contains information about the display window and two models, geometric and for displaying. The model from C3D file is represented as MBModel class object. Let's stop on each more detailed. The geometric model is essentially a container for geometric objects, any of which inherits from the MBItem class object. MBItem class is stored in the kernel like this. MBItem is geometric model object. Elements such as solid, polygonal objects, local coordinate system, and even object insertion classes inherit from this class. The insertion class is denoted MB instance in the kernel, and it is represented like this. It stores not only information about the geometric object, but also its local coordinate system as well. With insertion contains an inter-assembly unit as a geometric object. It is represented an MBAssembly class object. MBAssembly class is stored in the kernel like this. Assembly unit is a model object that combines a set of other objects, but one MBItem belongs to only one assembly unit. For example, let's open the file crankshaft C3D. If you open the context menu of the display window, you can see that its geometric model contains 11 insertions. You can see that there are 60 geometry objects inside the assembly belonging to the first insertion. However, all these objects have some local coordinate system stored in the insertion. It allows you to transform all these objects as answer. For example, move 100 units along the y-axis. Now I'm going to demonstrate this. I move the y-axis by 100 units. you can see that all the elements stored inside the first insertion have been moved 100 units along the y-axis. Among these 60 geometric objects, there is an object called solid, so that is a solid body. This is an object of class MBSolid, which just represents one of the detail elements, while the remaining 59 elements are just auxiliary geometry. It's used to create with solid and saved it, then the model is imported into C3D format. In order to get better understanding of MB model class, let's look at the code from the function make_user_0. First, let's read the model from the file crankshaft plus C3D into model, an object MB model class. It is more convenient to use the import from file function to read a model from a file. This function has an output parameter, which is a reference to a model in this case. It is convenient to do this. There are several MB item objects in the model. So I declare the model, neck the path, and read the model from the file, use it import from file immediately into the model. In the future, I will use the methods of our test application to render the model. You will have to override them in your projects. These methods make the following. Add a model to geometric model of the active window. Create a flat-faced model based on it, which I will talk about a little bit later. Display the flat-face model using OpenGL. So I grab the pointer to the active window, remove the old model, add model object to the active window model, fill the flat-faced model, calculate the size of the model, and display the flat-faced model. Now let's look at the result. I run the code, and you can see that the following appeared on the screen, such a multicolored model of the crankshaft. Now let's create 6 copies of the first element of the model, arrange them in a certain way, and add them to the model. I will uncomment the next part of the code. I take the first element from the model, duplicate it, put it in an array of new solids, move each solid rotated by a certain angle, and if this object is a solid, change its color, then increase the angle of rotation. However, these new solids have not been added to the model yet. In order to add them to the model, I need to uncomment the following part of code. You can add an object to the model using addItem method. Let's take a look at the result. And let's run user command 0. As we can see, 6 new Ember items objects appeared in the model. Now let's save the modified model into the file. It is appropriate to use the export into file function to save the model. It has a reference to the model as an input parameter. To show you how to do this, I will uncomment the following part of the code. I set the model into the file, and if successful, the code displays a text message. The model is written to the file fillet to C3D. Let's take a look at the result. As you can see, the model was successfully written to the file. Let's make sure that it is really written in the file fillet to C3D. I should open it. As you can see, this file contains the model from the previous example. To demonstrate direct modeling methods, I have got the file fillet C3D. Let's repeat all the actions above to the table model from this file. I change the file path to path2 and repeat all the previous steps. Let's look at the result. Now the table appears gray in the center, and 6 colored tables are located around it. Pay attention to the edges with fillets on each table. Now let's remove the fillets edges from each colored table. I'm using the face modified solid function. It allows to make direct solid modeling by modifying solid faces. For this, I uncomment the next part of the code. So I grab a geometric object, check if it is a solid, prepare in advance an array of fillet faces to be removed. Now, in the direct modeling parameters, I define a modifier responsible for removing fillet faces and run the face modified solid function. If have removed correctly, I change the solid to the solid without fillets. Let's look at the result. Now, as you can see, each colored table has no fillets, and the gray table has all the fillets. To demonstrate the result of triangulation in the model, I need a model of plinths. Let's read it from the file using import from file function. It takes the first parameter as a reference to ember item, so I can immediately replace the original geometric object of the model. It's the table in the center with this element. Let's uncomment the next part of the code and take a look at the result. If everything is made correctly, then a table should appear in the center. Instead of the plinthus, you can see it. As I said earlier, the geometric model has its polygonal copy to render itself. It contains polygonal copies of each geometric object contained in the geometric model. Each polygonal copy is an object of EmberMesh class. EmberMesh class is represented in the kernel like this. In fact, EmberMesh is container of triangulations. Triangulation is an object of EmberGrid class, which consists of a set of points and triangles. Triangulation describes the geometric shape of objects with a certain precision, and it is used to render geometric object, of course. For each geometric ember item object of the model, I call the gridMesh method, which creates an object of the EmberMesh class. A little bit later, I will talk in more details about the parameters of this method. Finally, I render each triangulation of this object. To demonstrate triangulation, I uncomment the last part of the code. So I go through the model objects, check if the object is not null. I create a mesh from it, calling createMesh method on each object. If it succeeds to create EmberMesh object, I render the triangulation of this object. I want to note that one EmberMesh object can have several triangulations, so I render each triangulation. Let's take a look at the result. As you can see, all objects are covered with a green grid of triangles. In order to better see the grid, I zoom with 10 and call this command again. These are the triangles that are rendered by OpenGL. Now let's talk in more details about the kernel methods available for polygonal objects. Please pay your attention to the code from user command free function. First, let's open the mesh C3D file containing an object of EmberMesh class. I will display mesh using the standard means of our test application. You can also override them. I call the code from a user command free function, and you can see the polygonal object. To make sure of this, I change the rendering mode to one frame. You can see that it contains of triangles. Let's create a new cylinder as an object of cylinder surface class and use the latter to make a polygonal object. To create a polygonal object by a cylinder, I use the calculate mesh method. Step data parameter determines the triangulation step along the deflection arrow. Form node parameter indicates that while creating a polygonal object, it is required to build a surface triangulation and not to build surface contours. So I will uncomment the following part of the code. To create a cylinder, I need to know its local coordinate system. The center of the system, radius, and height is required. I build a cylinder. When I prepare the mesh, prepare data for calculate triangulation step, set them, and try to build a mesh using the cylinder. Let's take a look at the result. Before, I need to render the second mesh. You can see that the second polygonal object has appeared. Make sure that this is a polygonal object can be calling the warframe mode. The fundamental difference between the second object and the first one is that the second object is not closed, and the first one is. Let's call inspectMeshClose method for each polygonal object. This method tests polygonal objects for closeness. To show you that I uncomment the following part of the code. So, if the inspector determines that the first object is closed, it will report that the polygonal object is closed. If the inspector determines that a second object is not closed, it will also report that. Let's take a look at the result. Polygonal object 1 is closed, which is correct. Polygonal object 2 isn't closed, as it should be. Now I replace the second mesh with a closed mesh. Read from the mesh intersection +5. I uncomment the next part of the code and also comment out the check of the meshes for closure to speed it up. So replace the mesh 2 with a mesh, read from the mesh intersection +5. Let's take a look at the result. You can see where the second object has been replaced with its part of a pipe, which is also a polygonal object. To make sure of this, I call a different rendering mode. This object also consists of triangles. Now, for polygonal meshes, I call create boolean method with the boIntersect parameter, which creates a new polygonal object as the intersection of the polygonal objects, and comment the next part of the code. I also need to add a new object to the model. Let's take a look at the result. You can see the intersection of two polygonal objects. This is also a polygonal object. To make sure, I call the wireframe mode. Change boIntersect to boDifference. Oh, sorry. boDifference by boIntersect. Let's take a look at the result. You can see the difference is also built correctly. Finally, let's turn to mesh intersection method. It builds the intersection contour of two polygonal objects as an array of polylines. I uncomment the following part of the code. Next, I call mesh intersection function, put the result into an array of broken lines. Now, let's render this array. For this, I uncomment the last part of the code. In order to see only the cursor, I comment back on the result of the logical function. Let's see what happens. You can see that the result is 8 broken lines. There is a tool in the functionality of our kernel which allows you to determine quickly collisions of geometric objects, for example, MBMesh polygonal objects. MB Collision Detection Utility tool is an utility to calculate quickly the intersection and proximity parameters of solids. To explain how it works, I need the code from make user command for function. I show you how the detector works using the example of two solids, although a similar result can be obtained for other geometric objects. I will use the standard functionality of our test application to demonstrate how the collision detector operates. The collision detector requires information about the transformation matrix to the global coordinate system for each solid. I will store it in the path matrix type variables. Each variable stores the transformation matrix and the path to the object as an array of simple names. After highlighting the selected solids, I declare the collision detector CDET and the collision detection utility in a class for fast collision detection queries. So I get the first solid, save its matrix in passform variable, and then highlight it. Next, I get the second solid, save its matrix in the passform true, also highlight it. Now I declare a collision detector and then create an intersection request with a function that processes the found collisions. To define a custom collision response, you should create a query that inherits from the CDET query structure. This is a structure of data and callbacks for a collision such query. I create a call query request. It will be processed when you call check collisions method, which checks collisions between geometric objects. Call query request must contain a callback function with a specific signature. Let's take a look on the structure of this request. It defines the response to the intersection of objects inside this function. The method here works as follows. You call the query if there is an intersection of faces and the code returns CDET intersected. Then the code renders the face of the first solid in red and the face of the second solid in blue. The code also returns the value cback search more, and it keeps searching footer among other faces to tested solids. Callback function itself is called query func. It has three parameters. Query is the actual collision search query itself. Code is the type of event that occurred as a result of the query. And the CData is a variable that contains information about a pair of objects which are processed as a result of this request. In this case, faces are used as a pair of objects. cback is the return value. So if the request is not null and the faces intersect, then the code renders the face of the first object in red and the face of a second object in blue and keeps searching. If no intersection found, then cback is set to cback void and the code stops searching. Add solid method of the CDET objects adds the solid to the tested for collision and then transformation matrix as well to the global coordinate system. Finally, depending on what value check collisions returns, I display the message in the status bar. So if the intersection is found, when the status bar shows then the text found intersection. Otherwise, it shows no intersection. Now, let's take a look at the result of this method. First, I opened the model prepared for collision testing. The model contains two objects, a table and a chair, which intersect, as you can see in the advance. The table leg intersects the seat of the chair. Now I run the code from user command for select the table, select the chair, and when you see the faces being intersected are highlighted. The edge of the table is red, and the edges of a chair are in blue. The status bar is showing the text found intersection. Let's check if the method is correct by moving the chair by 20 units along the y-axis. I move it in such a way that the objects don't intersect. When I run the code from the user command for again, select the table and the chair. You can see the edges are not highlighted and the intersection isn't found as event sent by the text in the status bar. That's all from my side. Thank you for attention.
Good day, my name is Ksenia and I'm a member of C3D Converter team. And now I'll show you how to use our converter function most efficiently. I'll show you this process using our test application. Converter functions allow you to write and read models of various formats, and there are some features here. Let's take a closer look at them. We will start with an easy one. Let's read the model of step format and add it to the viewer. I will do this by redefined command 0. We see that the model has been loaded. How did we do that? We use import from file function. As it is function parameters, we specify the path to the model itself and a pointer to the resulting root element, object of item SPTR. If you go to the description of item SPTR, you can see that this is a smart pointer to MBItem object. MBItem is a base class for all objects such as bodies, assemblies, wireframes, meshes, and so on. Accordingly, by accessing to the root element, we can access the entire model, the entire structure, and perform any operation with them. So, as a return value, the function gives a return code, by which we understand the import status, whether the model has been read correctly or if any errors have been occurred. If we go to this enum, we will see error options, no license, no object in the model, wrong extensions, and so on. In our case, the function returns the success code. It means the model has been read correctly. Therefore, we're adding the model to the viewer. We do it with separate function add content to manager. Here the object has been added to the viewer and some visualization settings were made. So what else can we do with the imported object using converter functions? We can write and read this model through the buffer using export into buffer and import from buffer. The return code for this function is similar as for import from file. We pass the C3D exchange buffer object to this function. This is a standard buffer with memory management implemented. An important argument is the format in which we write this buffer. In this case, we also have enum for all supported formats: set, GT, XT, STL, and so on. Let's try to write the model to the buffer. Everything has been written correctly. And next, let's try to read the buffer into another object. Let's see, everything is okay. And now, as an experiment, let's try to write this object to a file with incorrect extension. To do this, we pass the object to the export into file function and see what we get. As expected, unknown extension error is thrown according to the return code. What else? You can work with C3D exchange buffer object just like with a normal buffer. So you can write this buffer to a file with a standard function of stream write. Let's see the result. The file with the set extension has been created, and now let's try to read this written file with our function import from file. And now we see an error. Why? Because the file has a set extension, and the source buffer is in C3D format. Accordingly, if you change the buffer extension to C3D, then everything will be read correctly. Those were the main features. Next, I will talk about some extensions. So, import from file function can use not only item SPTR object I'll talk about in the previous function, but also C3D model document. And this is a more extended object which has not only a pointer to a root element, but also some additional data. To pass the model document to the viewer, we use getContent method, which returns a pointer to a root element. Let's see how reading a file into a model document will work. We read the model as in previous function. But why do we need a model document? The fact is that the C3D format supports a certain set of data, but other formats such as STEP, SAT, GT, and others can contain much more information. We read this information and pass it to the user, but not all of it is stored in C3D file. The most striking example is PMI. If we go to the model document class definition, we will see the function get annotation items. It allows us to query the vector of map of visual items. This is a vector of MA annotation item, the base class for all annotation types. So when writing to a C3D file or opening in our test application, all these annotations are not saved. To save it, we need to convert them to polygons or edges. And to do this, you need to use such a tricky structure. Here are the objects that convert MA annotation item to MB item, more precisely to polygons or edges. If we add this line to the module document constructor, we can see what imported PMI looks like. And now let's see how the same model with converted PMI will look like. Now we have PMI. In the properties, you can make sure that they are represented as polygons. The import and export functions can also take on property argument. Let's go to the class definition. Here is a list of possible settings such as stitching accuracy, whether similar phrases should be merged or not, object filtering, and others. You can customize all these things. And now let's see how the same file will be loaded with different options. Read the model with default settings. So the body and some 3D curves have been loaded. And now let's disable reading of 3D curves. It could be done with set EU permission function. We need to specify the type of object to read or write and the permission flag. If we go to that enum, we will see that the different types of object are represented here: bodies, surfaces, curves, attributes, dimensions, and so on. And reading and writing permissions are configured separately. In our cases, we pass the settings to the import function, so we are disabled to read 3D curves. Let's see what the model will look like in this case. As you can see, only the body has been loaded. What else might this property be needed for? For example, GT models can contain both BREP and polygon representation. Often, both of them are stored in the file, but not always. For such cases, we also have settings reading and writing BREP or polygonal representation. By default, everything is set to true. Accordingly, when reading the GT model, we first try to read the model as BREP, and if there is no such data in the file, we try to read the polygonal shape. But if you want to read the model in polygonal shape, ignoring the BREP, you need to use property. Now let's see how the GT model will look like with default setting. As we can see, the model has been loaded as BREP. And now let's disable BREP representation. Now we see the same model represented as by polygons. Pay attention to a progress bar at the bottom of the viewer. This is also an object that can be passed to the import or export functions. You can also redefine the progress indicator function as you like. And finally, I want to tell you about such useful thing as duplicate of model document. What is it and why is it needed for? Sometimes when models are exporting, the errors occur and resulting model doesn't look like it should. In this case, you give us the original model so that we can reproduce and fix the problem. In most cases, it will be enough to give us the original model, for example, in C3D format. But as I said before, the C3D format doesn't support some data, for example, PMI. This makes it harder to reproduce the bug. And to simplify the process, we can write the duplicate of the model document before exporting model into a file. We do this if the option debug settings save model twin is set to true. And now, before writing the model to the specific format, we said the function saves a duplicate of the model document in the separate files. You may send these files to us and we can read it in a specific way, restore the context of the error, and unambiguously reproduce the export error. Let's see how it will look like. We are reading and writing model. Yes. As you can see, the set model has been written to the specified path, and there are two files next to it. The twin of the model document with a C3D extension, and this is a duplicate, and the file with options. Now you can send these two files to us and we will be able to solve the problem much faster. I also wanted to say that there are many different examples of using converter function in the test converter CPP file. That's all from my side. Thank you for your attention and see you next time.
Thank you guys, Artyom, Ksenia, great. I hope you found this part useful. And that's all from us. So, by the way, all the participants will be able to get these recordings of the workshops. They will be also available on our YouTube channel, and we will also send the presentations to all the participants.
Well, we hope you enjoy our conference. We'd be very pleased if you left some feedback in our chat. Also, you can take some survey about this conference. You can find it by clicking the button called Take a Survey at the bottom of this web page, where you can see this broadcast. So, thank you for watching us. Also, we hope that you will attend this conference in the next year.
Thank you very much for joining. Thank you. Have a great day.
And see you next time. And
see you.
May C3D be with you.
Goodbye.